I feel like only the highest and lowest scorers take advantage of this strategy. The folks in the middle completely miss out. Erika here with Target Test Prep, and today I want to share a powerful but unexpected tip for GRE permutations, combinations, and probability. And then we'll apply that tip together in some of the hardest permutations, combinations, and probability questions in the Target Test Prep program. If you've watched my video on the hardest GRE quant questions, then you know that the topic that appears most frequently in the most missed Target Test Prep quant questions is number properties. But coming in at a close second is permutations and combinations. And I'm going to go ahead and throw probability in there as well, because probability problems frequently deal with permutations and combinations concepts. Now, when most test takers think about permutations, combinations, and probability problems, they think about the rules associated with them. Equations with lots of r's and n's and factorials, the slot method, very structured and regimented approaches to solving. And that's absolutely part of the puzzle. But a lot of students are shocked to learn that one of my biggest tips for GRE permutations, combinations, and probability problems is to use a little bit of brute force. And this is especially true on the hard problems. Now, if you're skeptical, I'll show you what I mean. This first question is permutations, and only 22% of Target Test Prep students get this right. All right, give the video a pause if you want to try this problem on your own. Now, taking a look at the question stem, we are trying to find a 4-digit number, A, B, C, D. Now, the number 1, 2, 3, 4 is different than the number 4, 3, 2, 1, is different from the number 3, 1, 4, 2, etc., etc. So this is definitely a permutations question. Now, continuing on with our question stem, we specifically want to find how many ABCDs we can form where the absolute value of A minus D equals 2, or in other words, where the first digit is either 2 greater or 2 smaller than the last digit. Okay, so at this point, most test takers, including myself, are going to set up 4 slots, one for each digit in our 4-digit number. So 1, 2, 3, 4. And then they're going to try and fill in the number of options for each one. Classic slot method. Okay, well, let's start. We have no restrictions on our 2 middle digits, so we'll start there. Each of those can be any integer from 0 to 9, so that's going to be 10 options each. Nice. But what do we do about our 2 remaining digits? Well, let's take a look at some of the ways that test takers mess this up. So first, the most obvious, about 10 to 15% of test takers make this mistake. They say, well, we can also have any of our 10 one-digit integers in the first slot. And then for each of those digits, we have 2 options for the last slot, one that's 2 greater and one that's 2 smaller. So we have 10 times 10 times 10 times 2 equals 2,000, or answer choice A. But that's actually not correct. Well, why? Well, you might realize that if we have a 4-digit number, our first digit cannot be 0, because that would actually give us a 3-digit number. So then you might say, okay, well, then I don't have 10 options for my first digit. I'm going to have 9 options for my first digit, or every integer from 1 to 9. And then I will still have 2 options for each of those digits for the last slot. So then I'm going to have 9 times 10 times 10 times 2, or 1,800, which is answer choice C. But that is also not correct. And around a quarter of test takers make that mistake. Okay, so why is that not right? Well, you might realize that for some of the smallest one-digit integers, 0 and 1, there isn't going to be another one-digit integer that is too smaller. And for the largest one-digit integers, 8 and 9, there isn't going to be another one-digit integer that is too greater. So in other words, while some first digits will provide 2 last digit options, some are only going to provide 1. So, okay. How do I account for that in the slot method? All right, let's hit pause before we waste more time making yet another mistake and take a look at our answer choices. The biggest one is 2,000, right? We already know it's not that one, but let's pretend. The biggest one is 2,000. Now we know our answer will equal 10 times 10, or 100 times however many permutations of our first and last digits there are. So the absolute largest number of first and last digit pairs we'll have is 20, right? 10 times 10 times 20 is 2,000. 20 is not that many. So why don't we just brute force them? We've already wasted way more time trying to find the right way to do this problem than we would have taken literally just writing our options out, which, if well organized, is going to be way less error prone. So let's just do that. Okay, so our options for our first digit are 1, 2, 3, 4, 5, 6, 7, 8, and 9, notably not 0. Great. Let's fill in our last digit options for each one. If our first digit is 1, our last digit cannot be too smaller, right? That would be -1. That's not a possible digit. So we only have 2 greater as an option, or 3. Okay, for 2, we can go 2 smaller. Our last digit can be 0. It's just not an option for the first digit. And we can go 2 greater with 4. Okay, continuing down, 3 gives us 1 and 5. 4 gives us 2 and 6. 5 gives us 3 and 7. 4 and 8. 5 and 9. 8, we can go 2 smaller with 6, but we cannot go 2 greater. 10 is not a possible digit value. And then same goes for 9. We can have 7. Okay, I now have all of my possible pairs of the first and last digit. So I'm going to go ahead and put an X in my first slot here to represent that we're taking these together. All right, so I'm going to count up my total number of pairs. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I have 15 first and last digit pairs. 10 times 10 times 15 is 1500, or answer choice E. Now, this is our correct answer, but note, if we had included 0 as a first digit option, we would have gotten answer choice D, which is a popular wrong answer with somewhere between a quarter and a third of test takers picking it. Now, my suspicion is that a lot of people who pick this answer do some element of brute force, but rather than write it out like this, they come up with their digit pairs. So 0, 2, 1, 3, 2, 4, etc., and then multiply by 2 because they can go in either direction, right? And they forget that actually this digit pair, 0, 2, only works in the opposite direction. You cannot have a 0 as your first digit. So this is another case of trying to save a little bit of time, right? And losing the question because of it. Writing out our digits as a part of the number like this helps us to not divorce the work that we're doing from the scenario it's a part of, which is unfortunately what happens here. Now, I timed myself doing this problem earlier, and the brute force part took 20 seconds. That's it. So the right way to solve this question and other questions like it is the way that is going to get you to the correct answer the fastest. And sometimes that's using a bad strategy, in quotes, like brute force. We're going to skip ahead to probability for the second question, and then we'll loop back around to combinations. Only 25% of Target Test Prep students get this next one right. Okay, again, give the video a pause if you want to try this problem on your own. Now, this question stem literally has the word probability in it, so it's pretty clear what we're dealing with. Now, like our last problem, we are dealing with number generation. So it seems like we are working with the probability of certain permutations. So there's going to be a lot of work that goes into this problem. I'm going to go ahead and set up a fraction bar as a reminder that I am solving both for a numerator on the top and a denominator on the bottom. All right, digging into our question stem. If a computer program generates 3-digit odd numbers using the numbers 9, 0, 4, and 1, and the digits can be repeated, what is the probability that the number formed from the program is a multiple of 3? Now, all of this stuff before the question target is describing the numbers produced by the machine, which is going to be our probabilities denominator. Let's start there. Okay, I know that the numbers produced by the program are 3 digits. So I'm going to go ahead and set up 3 slots. All right, starting with my last slot, I know that the number is odd, which means that the last digit is going to be odd. And then I know that the last digit can be any one of these 4 numbers. Well, the only odd ones are 1 and 9. So those are my only 2 options for my last slot, giving me 2 options for that last slot. Okay, moving on to our middle slot. Now, our middle slot does not have any restrictions other than that it has to be these digits. I know that digits can be repeated, so it can be any one of those 4 digits, or it can be 0, 1, 4, or 9, giving me 4 options for my middle slot. Now, note The question stem gives us these numbers in a really odd order, and there is no real reason for that other than to confuse us. So as I am writing these out, I am putting them in ascending order, and that's just going to make them easier to work with while I'm solving later. Okay, moving on to our first slot. Now we might think that the logic from our second slot applies here, and we're going to have four options again, right? 0, 1, 4, and 9. But just like in the last problem, we need to remember that the first digit of any number cannot be 0, or else we would actually have a 2-digit number when the problem specifies a 3-digit number. So 1, 4, and 9 work here, but 0 does not, giving us 3 options for our first slot or our first digit. Okay, multiplying that, we get 3 times 4 times 2, or 24 options for our denominator. Now, just like in our last problem, we're going to go ahead and take an early peek at our answer choices. Now, since we know that our denominator is 24, our answer must be a fraction that something over 24 could reduce to. In other words, its denominator has got to be a factor of 24. This means that we can rule out C and E, which is going to go ahead and put us ahead of the approximately third of test takers that choose one of those two answers. Nice. But just like in the last problem, this is also going to give us a clue at how we can solve. Our largest answer choice here is 1/2, 1 over 2, which is the same as 12 over 24. So this means that our numerator has got to be 12 or smaller, which means there are at most 12 permutations that make up our numerator. That's not that many. This means that a well-organized brute force strategy is a viable way to solve the rest of this problem. That's good to know. All right, so what do we even want for our numerator? Well, we're looking for the probability that the number formed from the program is a multiple of 3. So this is a number formed from the program. So once again, we're going to have a 3-digit number or 3 slots, and we want it to be a multiple of 3. Now, important to note here, a good way to find whether something is a multiple of 3 is to determine whether the sum of its digits is also a multiple of 3. If the sum of its digits are a multiple of 3, the number itself will be a multiple of 3. That is a huge help in solving this problem. But I have no idea how I'm going to fit that into my slot method. So yeah, I think I'm going to brute force, and I'm going to check back using my rule about multiples of 3. Great. Now I'm going to go ahead and leave these 3 slots here to organize my work, even though I'm not actually going to use the slot method, kind of like what we did in our last problem. Okay, I'm going to start with my most restrictive digit and work toward my least restrictive digit. Now, most restrictive is my last digit. I only have 2 options, 1 and 9. Going in ascending order, I'm going to pick 1 as my last digit. Okay. Next most restrictive is my first digit. I have 3 options, 1, 4, and 9. Again, going in ascending order, I'm going to pick 1. Okay, which numbers work for my middle digit in order to give me a multiple of 3, so such that the sum of my digits is going to be a multiple of 3? Well, if I put 0 in as my middle digit, I would have 1 plus 0 plus 1 or 2. Not a multiple of 3, not going to work. Well, what about 1? Okay, I would have 1 plus 1 plus 1 or 3. Hey! 3 is a multiple of 3. 1 is an option for my middle digit. Okay, what about 4? 1 plus 4 plus 1 is 6. Okay, that is also a multiple of 3, so 4 is valid as a middle digit. All right, what about 9? 1 plus 9 plus 1 is 11. That is not a multiple of 3, not gonna work. So for my numbers where I have 1 in my last digit and 1 in my first digit, I have 2 options that are a multiple of 3. All right, leaving my last digit a 1, let's go ahead and try a first digit of 4. Again, going in ascending order. Okay, the sum of 4 and 1 is 5. Let's check our middle digit. All right, 0 plus 5, not a multiple of 3. 1 plus 5 is 6. Hey, that's a multiple of 3. That means 411 is going to be a multiple of 3. All right, what about 4? 5 plus 4 is 9. Multiple of 3. 5 plus 9 is 14, not a multiple of 3. So once again, I have 2 options for a first digit of 4 and a last digit of 1. Okay, once again, last digit of 1, first digit this time of 9. Okay, this is going to give me a sum of 10 for my first and last digit. Trying middle digit options. 10 plus 0 is 10, not a multiple of 3. 10 plus 1 is 11, not a multiple of 3. 10 plus 4 is 14, not a multiple of 3. 10 plus 9 is 19, not a multiple of 3. So there are no middle digit options that work with these first and last digits. So there is no number that begins with a 9 and ends with a 1 that is going to be a multiple of 3. Okay, we have tried all of our first digits paired with a last digit of 1. Let's switch to a last digit of 9. Okay, going through my first digits again in ascending order, let's make the first digit 1. Now, before we go through our process again, let's recognize that this is the exact same setup as this, just in reverse order. We're going to have a sum of 10 plus these middle digits. We already know that that did not work. That did not give us any multiples of 3. So we already know that this isn't going to work. Okay, moving on. Let's have a last digit of 9 with a first digit of 4. Okay, 4 plus 9 is 13. 13 plus 0 is 13, not a multiple of 3. 13 plus 1 is 14, not a multiple of 3. 13 plus 4 is 17, not a multiple of 3. 13 plus 9 is 22. Careful. 22, not a multiple of 3. So once again, this isn't going to work. There are not going to be any numbers that start with a 4 and end in a 9 that are multiples of 3. Okay, last option. 9, 9. Okay, notice 9 plus 9 is 18. That is already a multiple of 3. So that means our middle digit is going to also need to be a multiple of 3 to give us a sum that is a multiple of 3. And you can just test that if you want to, but we know then that 0 is going to work as a middle digit and 9 is going to work as a middle digit, but 1 and 4 will not, right? A 0 is going to give us a sum of 18, a 9 is going to give us a sum of 27. So for this one, there are 2 options that are multiples of 3. And that's it. Now, because we did this in a really well organized, really intentional manner, going in ascending order, using our digits from most restrictive to least restrictive, we know that we have gone through all of our options. We haven't missed anything. And we have 2, 4, 6 total options. So we can go ahead and put that in our numerator. We have 6 possible multiples of 3 out of 24. That is going to reduce down to 1/4, or answer choice B. Now, the brute force portion of this problem took a bit longer than on the last problem. I timed myself and it took more than a minute. But brute force is the only way to solve for the numerator, and our total time on the problem is still well within an acceptable time frame for a problem like this. Now, there are some slight variations on approach. There are some pretty cool things that we can do thinking about all of these numbers in terms of how they relate to multiples of 3. So thinking about 4 as a 3 plus 1, thinking about 1 as a 0 plus 1, and that can help with our math, speeding it up and making it slightly less error prone. But in any solution, you will be writing out all of the possible multiples of 3. So in this problem, brute force is both the right and only way to solve. This last question is combinations, and only 26% of Target Test Prep students get it right. All right, once again, pause the video if you want to solve this one on your own. Glancing at my question stem, I see that I am picking a dance delegation or a group. Now, in a group, order does not matter, so we have a combinations problem on our hands. The previous 2 problems dealt with permutations, so this one's going to be a little bit different. Okay, digging into my question stem, I see that specifically we want to pick a dance delegation of 4 people, and those 4 people must be chosen from 5 pairs of dance partners, so 10 people total. Continuing on with my question stem, I see that we have a restriction. 2 dance partners can never be together on the delegation. Or in other words, I can only choose 1 person from each dance partner pair for the delegation. Okay, and then I want to find how many different ways there are to form that delegation. Now, at this point, I was pretty sure I wanted to use my absolute favorite trick for restrictions on permutations, combinations, and probability problems, which is to take my total and subtract my restriction. So instead of solving directly for what I do want, instead I'm going to solve for what I don't want and subtract it from my total. And this is going to be a really great way to get around some of the nastiness that the test maker has set up for you. So in this problem, I would be starting with a 10 choose 4 combination to represent choosing 4 people from my group of 10 with no restrictions. And then I would subtract out my number of combinations where I do have partners together. And this would give me my number of combinations where there are no partners together. And this trick would work really great if there were only 3 people on the delegation. But with 4 people, things get really messy. With a 3-person delegation, we could have 2 partners from one pair. Sure, that would be our partners together. But with a 4-person delegation, not only can we have 2 partners from one pair, we can have 2 partners from 2 pairs. And that gets really complicated. There ends up being overlap between partners that have one pair versus partners that have 2 pairs. I've looked at this from a lot of angles, and in this problem, solving for what we don't want is just as messy as solving directly for what we do want. So while I love this trick, I'm not going to use it in this problem. And I'm not going to use the combinations equation, at least not in the way that I hope to. All right, in my previous problems, looking at my answer choices was particularly helpful, so I'm gonna do that now. And what I see is, well, if my answer is A, yeah, I could probably brute force 20 combinations, but if my answer is B through E, I definitely cannot brute force all of those. So I know that that is not going to be the end-all be-all solution for this problem. So, okay, my trick didn't work, my combinations equation isn't working for me right now, brute force isn't gonna work. So what do I do? Well, what we're not going to do is sit and stare at the problem, trying to materialize the right solution. A tip that I've seen from Scott here at Target Test Prep is to keep your feet moving, which I love. If you don't know the right thing to do something, because doing something can help you wrap your head around the problem or give you new insights into what's going on or open up a new avenue for solving. Doing nothing will result in nothing. So here I know brute forcing isn't going to get me the whole problem, but it is something. So I'm going to start as if I'm going to brute force the problem to see if it gets me anywhere. And if it doesn't, if I'm still stuck in 30 seconds or so, I'll either try something new or guess and move on. All right, I have 5 pairs of dance partners. I'm going to go ahead and visualize them as capital A and lowercase a, capital B and lowercase b, capital C, lowercase c, capital D, lowercase d, and capital E and lowercase e. So those are my 10 people from my 5 sets of partners. Okay, I have 4 spots on the team. I'm going to draw those out as slots. All right, I want to ensure that each person on the team is from a different pair. So let's try some options here. All right, in slot number 1, I could have, say, big A and little a, someone from the A dance partner pair. All right, in my second slot, I could have big B or little b. In my third slot, I could have big C or little c. And in my fourth slot, I could have big D or little d. So this represents a combination where we have someone from each of the first 4 pairs. All right, well, what other combinations of pairs could we have? Well, I could have an A again in the first slot, a B again in the second slot, a C again in the third slot, and an E in the fourth slot. That is another possible combination of my dance partner pairs. Continuing on with my combinations, I could have an A, a B, a D, and an E. I could have an A, a C, a D, and an E. Or I could have a B, a C, a D, and an E. So I can see that there are 5 different combinations of pairs that work here. But I know that that's not it, right? Because for each of these combinations of pairs, I can have a different person from each pair. Well, let's look at just this first combination. I see that for my first slot, I have two options, big A or little a. For my second slot, I have two options again, big B or little b. And then same thing for the third and fourth slots, two options for big C or little c, and two options for big D or little d. Now, because I'm looking at this specific combination, a combination where I have an A in the first slot, a B in the second slot, a C in the third slot, and a D in the fourth slot, I can essentially treat just this as a permutation. I can use my fundamental counting principle or my slot method. So I have two options for the first slot, times two options for the second slot, times two options for the third slot, times two options for the fourth slot, or 16 total options for how I can create a combination specifically where I have an A in the first slot, a B in the second slot, a C in the third slot, and a D in the fourth slot. Now, that same logic is going to apply to my second combination. I have two options to put an A in my first slot, two options to put a B in my second slot, two options to put a C in my third slot, and two options to put an E in my fourth slot, for again, 16 options total where I have an A, a B, a C, and an E. Now, if I extend this logic down, I'm going to have 16 options for each of these 5 combinations. So 5 combinations of pairs times 16 options each gives me 80 total combinations fitting my restriction, or answer choice E. Now, reflecting on what I did here, I essentially took my 5 couples, my 5 dance partner pairs, and I chose 4 of them. And then I recognized that for each of those combinations of 4 couples, I would have 2 times 2 times 2 times 2, or 2 to the 4th arrangements or permutations. So essentially what I did was I had a 5 choose 4 combination, 5 couples, choose 4 of them, times 2 to the 4th for each of those combinations. And that gives me my answer of 80. Now, if that math occurred to you immediately, congratulations, that's great. You're going to solve this problem a lot faster than I did. But if it did not occur to you, and I'm going to bet that it didn't, this problem illustrates the power of using a little bit of brute force as a galvanizer to get the gears turning and to get ourselves unstuck. Now, there is one other method to solve, and it's actually the one used in the Target Test Prep program. I'll be honest, it did not occur to me, but it does work quite well and quite quickly. So if you think you know what it is, comment down below and I'll tell you if you got it or not, and I'll explain why it works. So what can we learn from these questions? Well, while brute force rarely works as a permutations, combinations, and probability strategy in isolation, when deployed sparingly and strategically as one step in a larger problem-solving process, it is immensely powerful for solving quickly, for avoiding traps, and for getting unstuck. And it's even sometimes a necessary step in reaching our answer. Were you able to solve these problems on your own? Go ahead and brag about it in the comments. They were hard. And if this video helped you, go ahead and give it a thumbs up so we know to make more like it. Thanks for watching, and I'll see you in the next one.